Test, 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 test.
Should I monitor the stream from here?
Be sure and signal me when I need to actually start. Hi, everybody. I'm Rick Hartley. Thank you for attending this session on how to achieve proper grounding in PC boards. We're going to wait just a couple more minutes for a few other people to log in and to attend. In the meantime, some of you may know who I am. I've been to Europe a number of times to do presentations around that part of the world. And some of you, again, as I say, may know who I am from those presentations. I'm going to be doing 2 next May in Amsterdam and Paris. So that would be an opportunity. If what you see today appeals to you, that's an opportunity for you to get some additional knowledge along the lines of this material. Start. And as I said, it's time to get going on how to achieve proper grounding in circuit boards. In 2 seconds, I've been in industry for 55 years. I've made all the mistakes you can make, and fortunately along the way I learned how to do a few things properly. I do want to start by apologizing for the fact that I have a cold. I know my voice sounds terrible. I'll try my best not to do any coughing, but I can't make any guarantees, so apologies for that. Anyway. Pause?
Yeah.
We're on pause? I'm going to pause for just a moment. My apologies. For questions, I hate to say it, but
No, I mean, you can still. Okay. Just apologize that we.
yeah, I will.
Can't
Are we
see
ready?
now. Yeah.
Okay. Hi, everybody. Welcome back. Sorry about the delay. We ran into some technical difficulties, and I'm sorry to say we're getting started 15 minutes late as a result of that. Anyway, going back to where we were, this session is on how to achieve proper grounding in PC boards, and the concept of ground will become quite apparent as we go through the material. The term ground really refers to the earth, as I'm sure everybody knows, because initially the earth was ground for a lot of different things. For example, 200-300 years ago, we realized that we could use a rod on top of a building with a nice hefty wire sinking deep into the ground to cause lightning to divert away from the building to avoid burning down structures. And this worked out very well, and it was one very perfect use of the earth. It was soon realized that we could use earth or the ground as a return for other things. For example, in the early days of telegraph, they had two wires running between all the poles. And at one point, someone realized, and I'm not sure when exactly this happened, that they could, by hooking up the internal circuits ground to the box, sinking the box deep into the earth, that they could use the earth as a return path for telegraphy. Well, needless to say, when you can string one wire instead of two, this is a massive cost savings. And so from that point on, all telegraph that was strung throughout the world simply used a single wire. The earth is not a great return path for circuits, but when energy is high enough and when frequency is low enough, it works out relatively well. And so for many years, people used it for situations like this. They also used the earth in factories for returns for motor generator sets and some kinds of circuitry that were used in factories to run machinery. The automotive world has used the chassis of the car as a return path for low frequency, high power stuff for as long as we've had automobiles. And these concepts work in that environment. In the case of modern day electronics, about the only thing we use the earth for is the third wire of the AC lines coming in, the mains, if you will, coming in from the service entrance. They will hook the third wire to the chassis of metal chassis devices and hook the other end to earth. The concept being, of course, that if the phase line were to short to the chassis, you'll blow a breaker or a fuse as opposed to blowing out someone's heart when they walk up and touch the thing. And that's really the concept. It's a safety issue. Safety is its only value and its only role. It has no value with respect to EMI. That third wire, in fact, that third wire, if you don't hook it up correctly, if you don't add some inductance, the EMI problem. So that wire has no value with respect to EMI. It's simply there for safety purposes. A lot of EMI personnel I've heard over the years use the chassis, talk about the chassis as if it's a ground. In fact, the chassis is simply a Faraday cage. The purpose of the chassis is to contain fields and keep them in the box and keep fields outside the box from getting in so that we won't suffer from interference problems. But the chassis is in no way a quote-unquote ground, even when we attach it to the earth. From a high frequency standpoint, that long wire attaching to the earth, or even mounting the chassis to a metal frame to the earth, is not a low impedance attachment at high frequencies. So the earth is not a good ground for anything at high frequencies. Ground on PC boards is often considered a region of 0 volts with 0 impedance and 0 resistance. And I hope everyone watching this knows that that is simply untrue. It's only close to true at DC. At DC, where we basically have no frequency, of course, only at that frequency does ground appear as a really low impedance. At any frequency above that, it is not. I can't read it. Pause it, can you? course. Sorry, guys. Again, minor technical difficulties. Anyway, the concept is only close to true at DC. Ground is often thought of as a place to drain off or eliminate noise, as if it's some kind of magic sinkhole that we can use to get rid of energy that we don't want. And of course, that's simply not true. The concept and belief that many people have about ground just does not exist. I was once one of those people who foolishly believed that ground could be used to drain off and get rid of excess energy that has no value. We'll talk about all that in detail as we go through this. The turning point in my life came when I met a gentleman by the name of Ralph Morrison. Ralph attended a class that I did about 16 years ago. It was a one-day class, and at the end of the day, he came to me and he said, "Rick, I'd like to take you to dinner and talk if we could." I said, "Sure, Ralph, let's do that." And over dinner, he said to me, "I like a lot of the concepts that you teach. You really have some good ideas in your material." But he said, however, there's one thing that you are teaching that's probably not correct. In fact, he said it is definitely not correct. And with that in mind, he asked me the question, what is energy? I gave him some half-baked answer out of a physics book as best I could remember from college. And it was something to the effect of what you see on the screen here, that it's basically molecules in motion, doing work, yada, yada, yada. And he smiled and we said, yeah, that's pretty much what energy is. Then we talked about the fact that energy exists in many forms, that it can be mechanical, light, heat, electrical, so on and so on. And you can convert energy from one form to another, but energy is never lost, nor is it destroyed. And we discussed all this at length. And by the way, something we didn't discuss, but I want to throw it out here just to make sure everybody's aware of this. The only difference between light energy and electrical energy is frequency. And I know some of you are thinking, wait a minute, light that illuminates the room and electrical energy that runs
Now that
Now they are?
Yeah.
Oh, brother.
Start from the
Wait, still pause it. So can they see this computer? Anyway, going back for just a second, energy exists in many forms, and Ralph and I talked about that, about the fact that it can be mechanical energy, light, heat, sound, and so on, and all that really happens, you can convert energy from one form to another, but you never actually eliminate or create energy. It's simply a matter of moving it from one type to the other. And one concept that I want to make sure everyone understands is that light energy and electrical energy are really the same type of energy. The only thing different between them is frequency. And I know some of you are thinking, wait a minute, light energy that lights the room and electrical energy that runs down wires are the same thing? The answer is yes. The only thing that separates them is that light is an extremely high frequency compared to electrical energy. So then Ralph asked me, where does energy exist in a circuit? Is it in the voltage or is it in the current? And I thought for a moment and I said, well, Ralph, that's a great question. If the, in power delivery, we have a relatively constant voltage and we vary the current. The current varies wildly in amplitude and frequency as you move energy into and out of IC. So it must be the current. That's it, Ralph. The energy's in the current. And Ralph smiled and looked at me and he said, no, actually, Rick, it's neither. Energy doesn't exist in either voltage or current. Reality is the energy exists in the fields that are in the circuit. The fields that travel, the electric and magnetic fields that we all know about. And basically, there's no energy in the voltage or current. All the energy is in the fields. Then he asked me, where do the fields exist in a circuit board, for example? Do they exist in the traces, or do they travel in the planes? And I said to Ralph, wow, that's a great question. Now I was really, really stammering, trying to figure out what the heck the answer was. And he smiled at me and he said, I'm messing with you again, Rick. It's neither. The fields don't exist in either the copper of the traces or the copper of the planes. The fields exist in the dielectric space between the signals and between the planes. In the plastic and fiberglass, for example, in FR4, the fields move in the plastic and fiberglass of the board material, not in the copper. So what I'm saying is all of the energy in a circuit moves in the plastic of the circuit, not in the copper. The copper acts as a waveguide to steer the energy from point A to point B. The copper, as you route a trace across the board and it references a plane, the fields will follow that trace and plane from point A to point B because it's a lower impedance path than it would have to follow if it were just launched into the board. Could we just launch the energy into the dielectric? Yes, we could. We do it all the time in air with radio broadcast. That's exactly what radio broadcast is it's energy being launched into free space so that it gets picked up by antenna at the receiving end so people can listen to it, or in the case of television, watch it, or so on. We do it with Wi-Fi, we do it with virtually everything that's a broadcast medium. We could launch the energy into the circuit board dielectric. The advantage of giving it a trace to follow is that offers a lower impedance path, and that's the concept. And once Ralph got this concept into my head, suddenly everything that I had ever believed about how circuits function changed, and I suddenly understood exactly why everything that I'd ever experienced that went wrong, because we were failing to control and contain the fields. We weren't keeping the dielectric space small enough. I have a friend, Dan Beeker, some of you may have heard him talk, where he has a song he sings, or his daughter sings actually, to the tune of Meghan Trainor's It's All About the Bass. And he sings It's All About the Space because it is all about the space. If you aren't controlling the space, you aren't controlling the fields. What is this? I just said that the trace and plane on a board are a waveguide. This too is a waveguide. It's a tubular waveguide made out of metal. If you attach energy to this, and this isn't how you would do it, but if you were to launch energy into this tubular waveguide, where the half wavelength point was equal to the dimension x, which is halfway around that tube, you'd get a standing wave of energy in that tube, and that energy would transmit down the tube from point A to point B, allowing the energy to move from the transmitter, in this case, to the receiver. The beauty of a waveguide of this type, it's designed to transmit one frequency of energy only. Any stray energy that's attached to that will basically get shorted to the metal and won't appear as a standing wave in the tube. This too is a waveguide. It's a waveguide that's built into a circuit board using circuit board material and the copper of planes. In this particular case, the waveguide has a slower movement of energy because the higher dielectric constant slows the energy down, but it still functions in exactly the same way as the air dielectric tubular waveguide. The energy launched into this will move through it one frequency only, just as it did with the tubular waveguide. Notice that feeding this is a microstrip trace. There's a microstrip trace above a plane. And the reason this works is because the microstrip is also a waveguide. A trace and a plane form a waveguide just as do a a perfectly structured waveguide designed to conduct one frequency. The difference between a microstrip trace or a strip line trace, which is interlayer, referencing a plane, is that those structures can send multiple frequencies. We're not limited to a very narrow frequency range as you would be with a waveguide as shown here. A transmission line is any pair of wires used to move energy, any pair of wires or conductors used to move energy from point A to point B. There's a voltage across the copper features. There is current in the features. The energy, the E and H fields are in the dielectric, meaning all of the energy is traveling in the dielectric between the copper features. And it establishes a voltage across the trace and the plane, and it establishes a forward and return current in the copper features as it travels. I've had many engineers tell me over the years when I ask them, how does the circuit work? They'll say, well, the current is launched into the trace by the driver, it goes down to the receiver, and then returns in the return path back to the driver. Not true. The fields move through the dielectric. They're launched by the driver. They move through the dielectric and they establish a forward current and a return current in the trace and the plane simultaneously. So as the energy has moved 1/3 of the way down this transmission line, it has formed a forward current and a reverse current simultaneously in the first third of the copper structure, but there's no current in the rest of the structure. There's no voltage in the rest of the structure yet because the energy hasn't reached that far down the transmission line. That's how things actually work in a circuit board. How we treat this return path, the ground as we tend to call it, is an extremely important aspect of designing circuit boards. This is a picture of a strip line trace, an interlayer trace, centered strip line between a pair of planes. When we move energy into this transmission line, the first thing that happens is the electric field appears out of the driver into the dielectric space, attaching itself to the trace and the plane. The energy that is in those electric fields forms a current, a forward current in the trace and a return current in the copper structure of the planes. And I've shown it here as a skin effect current, meaning it hasn't sunk all the way through the copper, implying that this particular set of fields are very high frequency. That's what happens at high frequencies. And that's a topic for another discussion, is to discuss skin effect losses and that sort of thing. But the current is shown here in yellow. The current exciting the electrons in the copper causes electrons to move from atom to atom in the copper, and the reaction from that is to form a magnetic field. Remember, all of the energy is in the electric and magnetic fields moving through the dielectric. This is an outer layer trace. You can see this is a simulation done in a tool. I won't mention which one, but this is a simulation done in a very well-known tool, as was the previous picture. And it shows that the fields on the outer layer are not as well contained. One of the reasons we tend to use inner layers for extremely critical signals is because of containment of fields, containment of energy. Very sensitive analog signals, very high-speed signals. On the contrary, though, when you have really short signals that you're only going to route between two devices, 10 millimeters, 15 millimeters, 20, 30, 40 millimeters, those kinds of things, no, I'm sorry, not millimeters, quarter of a millimeter, half millimeter, and so on. When you're going to route things very short distances, the reality is you want to route them on the outer layer. Even though the fields will expand more, it makes no sense to drop to a via, go to an inner layer, go a short distance, quarter of a millimeter across the board or a half millimeter, and then go back up through another via to the receiver. That makes no sense at all. So in cases like that, keep short signals on outer layers. It's a much better way to contain and control fields, and we'll talk in a short while about why that statement is true. This is a picture of a side view of a circuit board showing a ground plane on layer 2. This is the way the RF world would design what they call a microstrip board. There would be a ground plane on layer 2. There would be signals routed on layer 1. There will be power routed on layer 1. And all of the open area around the signals and power would be poured with ground copper and attached with multiple vias to the ground plane. If we rotate this 90 degrees and look at it as in the top view, assume there are multiple ICs on this board and assume that 2 of them are as shown in this picture on the corners of the board, and they have a trace that routes all the way around the perimeter of the board from one device to the next. Notice that both of these devices are attached to the ground plane in a single location. One of the things I do when I work with an engineer for the first time is I draw this on their whiteboard and I ask them the simple question, where's the return current from that signal? And unfortunately, about 70 or 80% of the engineers I meet say that the return current is directly between those 2 connections to the ground plane, directly across the ground plane from one IC to the other. If this were a DC level energy transmission, then that would be where the energy would travel. It would take that short straight path directly across the plane. At DC, it would also spread out, and it would spread out to a fairly wide swath. It wouldn't just remain in a tight location. The energy would spread out considerably. But as you go up in frequency, and get up into the 200-300 cycle hertz range, the energy would be more focused toward the transmission line. You go up to a kilohertz, 2, 3, 5, 10 kilohertz. By the time we were out of the audio range, all of the return current in this particular circuit would be directly under the trace following the forward current. The arrow pointing forward indicates the forward current in the trace, and the arrows pointing backward indicate the return current in the copper structure of the plane. And the energy would flow around that transmission line from the driver to the receiver with the forward current in the trace and the return current directly under the trace going back to the driver. That's how circuits work at frequencies beyond a certain range. And we'll talk more about frequency range in just a moment. So a question that comes up is, when the return path is directly under the trace, why does that happen? Well, the reason the path directly under the trace is the path of lowest impedance, meaning it's the path of lowest inductance and greatest capacitive coupling. Because impedance, for the most part, is the square root of L over C, inductance divided by capacitance. Let's talk about that a little more. Inductance. Let's define inductance and capacitance. Inductance is an impedance to change in current flow caused by the energy stored in the magnetic field. For example, imagine in your head that you have a circuit board with the forward signal on the top layer of a board and the ground also on the top layer, but 50 or 75 millimeters away, 2 or 3 inches, for those of you who still think in the imperial system. So 50 to 75 millimeters away from the trace is the return path, or the ground trace. In that particular case, the fields are going to have to occupy that large space, that large volume of space between those 2 traces. And the result is the magnetic field is going to be extremely large in size. And its extreme size will cause great inertia. And that great inertia will cause high inductance. So how can we lower the inductance? Well, I was taught in college that if you make the copper features larger, that we can reduce inductance. And that is a true statement. If you make the copper features larger, it will impact inductance. Unfortunately, you'd have to make the features larger by 40 or 50 times just to lower the inductance by 25 or 50%. The easiest way to lower inductance isn't to make the copper features bigger, it's to bring the features closer together. If we move those 2 traces that are separated by 75 millimeters down to 1/4 of a millimeter or 1/8 of a millimeter, where they're 5, 10 mils apart, we're going to reduce the inductance by several times to a much lower level. Why? Because we will be containing the magnetic field. It's all about the space, as Dan Beeker would say. It's all about the space. The best way to lower that impedance, that inductance, is to put the trace directly over a return plane. Have a return plane in the board on the next layer of the board and route that trace directly over that return plane. That will minimize the magnetic field to its lowest volume, hence minimizing the inductance. Capacitance is the same way. You can get maximum capacitance by having the forward trace as close to the return path as possible. And remember, the goal is to achieve a low and controlled impedance. Low inductance, reasonably high capacitance. We achieve that by routing signals right next to a ground plane on a board. Okay, then, why did the low frequency return current spread out? Let's just get right to the point. Let's get right to the point. The full equation for impedance, I showed it as the square root of L over C. It's actually more complex than that. It's R plus J omega L divided by G plus J omega C. R being resistance of copper. Think about what happens at DC. What's the impedance due to inductance in the numerator of that equation going to go to at DC? It's going to go to 0, which means that the numerator at DC will be dominated completely by resistance. So in other words, at DC, the energy will follow the path of least resistance. And the path of least resistance is a wide swath area. It's a fairly wide area that the energy will follow as it tries to move through the circuit board. And as frequency goes up, L will start to have a role. And as it goes up further, it'll have a bigger role. And at some point, L, inductance, will dominate performance, and energy will then no longer follow the resistance path. It'll follow the path of lowest inductance. And that's exactly what we illustrated with that slide. Here's a simple experiment you can do in your lab to be able to test this concept. Hook a signal generator up to a 2-meter piece of coax and wrap the coax back around on itself so the open ends are close to each other, and tie the shields together with a 75 or 100 millimeter long wire, a 3 or 4 inch piece of wire. Put a load resistor on it, set the signal generator to some voltage output, 3 volts, 5 volts, it doesn't matter what it is, just set it to something. Start it at DC, put a current loop around the wire so you can measure the current in that wire marked as item D, and turn on the signal generator at DC. And what you will find is at DC, 100% of the return current from this circuit will be in that short piece of wire. Obviously, the forward current will be in the center conductor of the coax as it travels around that loop, but the return current at DC will be in the wire. As you turn up the frequency of the signal generator, it won't take long until you, at a few hundred cycles, you'll begin to see that the current in the short wire will become less and less as you go up in frequency. And by the time we get to 50 or 100 kilohertz, there will be literally almost no current left in the wire. There will be some, but it'll be minuscule at that point. And we're talking about a wire that is 1/30th or 1/40th the length of the coax, and yet by the time we get to 100 kilohertz, there's literally almost no current left in the wire. Here's a graph put together by Dr. Todd Hubing of Clemson University that illustrates exactly that. And you can see that at 100 kilohertz, there is a trickle current left in the wire. By the time you get to 1 megahertz, there is no current left in this short piece of wire. All of the return current will take the 2-meter path and will ignore the 75 millimeter path, simply because at higher frequency, energy follows the path of lowest inductance and highest capacitance. That's how it works. All of the circuits you work with in the digital world today, regardless of clock frequency, are high frequency circuits because it's all about rise time. Rise time is what dominates frequency in digital circuits, not the clock frequency. I've seen many companies make the mistake of thinking, oh, we only clock at a few megahertz. We have nothing to worry about. They ignore rise time. They lay out simple 1 and 2 layer circuit boards that don't have adequate grounds, adequate return paths, and they get themselves into huge trouble as a result of it. Don't make that mistake. Everything that goes wrong, all EMI, all signal integrity problems, all crosstalk, everything that goes wrong happens during the rising and falling edge of signals. And it really is not associated with the clock. So keep that in mind. So frequency today in digital circuits, regardless of clock, is measured in the hundreds of megahertz and up. Everything you use in the digital domain, even the slow microcontrollers, have rise time frequencies in the order of 100 megahertz or more. So everything you're doing is high frequency. Keep that in mind. This is a circuit board that was designed for a robot in 1984. Wish I had more time. I could tell you a wonderful story about this robot, but anyway, I won't. The trace that's pointed to with the arrow, back in 1984, if energy was launched from one of these ICs into that trace to move to another IC, and at that point in time, the fields off of that trace would have coupled across that entire dielectric region, and they would have coupled most of the voltage and most of their current into the power trace, which is that fat trace at the top of the row of ICs, and into the ground trace at the bottom of the row. In other words, most of the return current at those frequencies in those days would have been in the power and ground rails that we routed on the board. This concept worked extremely well in 1984. If you put a signal at today's speed into that transmission line, the fields would only couple 1 or 2 traces away, meaning that all of the return current would be in the traces immediately adjacent to this target trace. The fields would not expand far enough at high frequencies to be able to reach the power and ground traces. And the end result would be that there would be no return current in power or ground because their impedance would be too high relative to the forward trace, and the end result is the energy would never get there. All of the energy would return through the nearby traces. And this is a problem that we see today in some designs. There are a lot of people who still want to design 1 and 2 layer boards in this style. And at today's frequencies, this is a really bad plan because it can get you into deep, deep trouble. Let's look at a pair of twisted wires. If we have a wire pair shown here, and I put energy in it regardless of frequency, the energy is going to follow the wire marked as plus because that's the positive side, the output side of the driver. And the ground side, the return side, will be the negative wire. And the return current will be established in that wire marked negative. The fields will be contained in the dielectric space between the 2 wires. What happens if I add another wire? What's the result of doing that? What happens if I add a 3rd wire? Well, the answer as to what happens depends on frequency. If again, let's go back to the DC state. If I put a DC energy source and hook it up to this pair of wires that now has 3 grounds, at DC, if these 3 grounds are roughly the same wire gauge, and if they're roughly the same length, the current will divide equally among those 3 wires. This will be what we call a classic ground loop. Ground loops, by the way, exist at low frequencies. They don't exist at high frequencies, and you'll understand why in a moment. The current would split equally among all 3 of these at DC. Again, imagine a signal generator hooked up to this circuit. As we increase the frequency and get to a few hundred cycles, the current in that bottom ground wire is going to lessen. And at some point, we're going to increase the frequency to the point where there's no current left in that bottom ground wire, and there will only be current in the twisted wire ground and in that second wire. And eventually, we will reach a frequency, and this will happen before we are out of the audio range, long before we're out of the audio range. We'll reach a frequency where all of the energy will travel in the twisted wire pair, and it will ignore those other 2 wires as if they're not even there. I've laid out many circuit boards with grounds on every layer of the board. We do this in the RF world all the time. And I had people say to me, oh, you can't have a ground on the same layer as the signals because there's a ground plane underneath the signals. You're creating a ground loop, not at high frequencies. You don't create ground loops at high frequencies. The energy at high frequency will take only the low impedance path. That is the only path it will follow. You can provide, think about a ground plane. Why does a ground plane work in a circuit board driving digital devices? All the digital devices are operating in the hundreds of megahertz and up because of rise time frequency. So why does a ground plane work? Because the energy focuses itself directly under the trace. It doesn't spread out as it would at low frequencies. In low frequency circuits, you may need to actually consider routing ground if the frequency of the circuit is low enough and route it directly under the signal trace that's routing across the board. I've had to do that in the early days of my career when we were doing some very low frequency analog designs. That may be necessary at low frequencies. It is not necessary in the high frequency domain. This is a picture from Dr. Wu, who presented this material at the IEEE EMC symposium in the United States several years ago. And he brought these four figures up on the screen. And he said, imagine, if you will, that figure 1, that large gray rectangle is a ground plane on layer 2 of the board. And the cross-hatched line is a signal trace on layer 1. And imagine, if you will, that we launch a signal into that trace relative to that ground plane. The energy is going to be mostly contained. There will be some energy that will radiate off of the board because outer layer traces do radiate some amount of energy. It isn't much, but they do give off some energy. Now imagine, he said, you have 3 other planes, another solid plane, as in figure 2, but has a split in it. And then in figures 3 and 4, we have crosshatched planes. Look at figure 3. It's a crosshatched plane. However, underneath the trace, there's a solid area of copper, which means that figure 3, relative to the trace, assuming this is high frequency current, figure 3 relative to the trace looked pretty much like figure 1. So if you measure the EMI coming off of these boards, you would expect figure 1 and figure 3 to be relatively the same. He asked the question of the group, what is the order of EMI coming off these boards from least to most? And there was a large group, 100 and some people in the room, mostly double E's. And the answer that he got most frequently was that 1 and 3 would be relatively good, relatively the same. 2 and 4 would be worse. And a lot of the engineers in the room thought that 4 would be the worst example. Some of them thought that 2 would. Let's take a look at the EMI signatures of these. Here's 1 and 3. We said a minute ago, because of the solid area of ground underneath the signal on figure 3, it and 1 are going to be relatively the same. Here are 2 and 4. The gray line is figure 4. It's the one with the cross-hatched plane, it's the one with the cross-hatched plane where you're routing across the openings in the plane. And because of that, you would expect it to be slightly worse. But look at what happens in figure 2. The EMI signature of that particular board is anywhere from 20 to 30 dB worse than the EMI signature of 1 and 3, depending on what frequency you're looking at. 20 to 30 dB worse. That is an enormous EMI signature. That basically is a radio station. Let's look at the current, at a simulation of the return current in the planes as seen in these circuits. 1 and 3, just what you would expect. They have a return current that looks extremely similar. 4 does have a spread return current, which you would also expect because you're routing across the openings in the plane. Look at 2. Oh my gosh. I mean, look at that thing. The energy from that signal reached that split in the plane and went, uh-oh, I have no easy way to get across this gap. It's like reaching a canyon when you're on a hike. How are you going to get across? Well, you're going to have to find a bridge. So you go out of your way, you find something. But the point is the energy had to spread out across that entire gap, trying to find paths to get across the gap so it could continue on to the receiver. And as a result, the energy spread all across the board, radiated off the board. It even spread out to the outer edge of the planes, and the current spread down the edge of the planes, causing the edges of those planes to look like a dipole antenna. This board radiated literally like a radio station. In fact, I don't know how many of you are aware of this, but there are antenna engineers who will design circuit boards that look like this when their goal is to cause radiation. So, rule number one when designing a circuit board, never, ever, 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 ever route across the split in a ground plane. We're going to talk more about this as we go. So, never route across the split. Well, look at this. This is a two-layer board from the automotive world, where there's signals on one and signals on two, and they route across each other. If routing across one split in the ground plane is bad, clearly this has to be really bad. And the answer is yes, it's terrible. You absolutely cannot do this kind of design in today's world with today's speeds, IC speeds. This IC driving this is a microcontroller. And it is a slow device by today's standards. It probably has a rise time of 2-3 nanoseconds, which means that its frequency due to rise time is probably only 50 or 100, 200 megahertz. It's not a terribly high-speed device, but still 50 to 200 megahertz, somewhere in that region, is high frequency. You launch that energy across that split, and those constant splits are going to have a problem. And these people did have a problem. They contacted my friend Dan Beaker, whom I mentioned a little while ago. He works in the automotive industry, and he had his guys redesign this board. And I'm going to show you just the top of the board after it was redesigned. They rerouted all the traces so that all of the white traces you see in this figure are ground lines that were routed next to the signal lines. The idea being to create a coplanar ground, a ground on the same layer as the signals, so the fields had a path to which they could tightly couple to keep them from coupling through the board and into the gaps of the traces below. So it stopped the problem. It didn't completely stop it, because in reality, this is not an ideal guard trace. This is not what we want to do in an ideal circuit. This is clearly not a perfect guard trace, but it is so much better than what they had done that it gave them a 20-some dB improvement in their EMI signature. And these guys were delighted with the outcome. Notice that Dan also had them put a ground pour under the IC. Of course, you couldn't do this with a BGA, but with a microcontroller that has Gull-Wing leads or J-leaded, it's the J-leaded part or whatever, you could do this. Why did he do this? Because this IC was less than well designed as well. There are a lot of things in the electronics world that aren't well designed, and this IC is one example of a not well designed device. Notice there are a handful of ground pins. They're all marked in white. What do all the signal pins that aren't next to a ground pin, how do they get back into the IC? Do they use ground? The answer is no. You want me to just, hey, Hi, how's it going? All right. So, sorry about the interruption again. We unfortunately have had another technical difficulty. Hopefully that's all. Going back to where we were just a second ago, as you recall on the previous slide, we had traces routed over other traces, which means many traces routing over many gaps. And of course, that's just really a bad plan. And they had a horrible EMI signature. Dan's group redesigned this board to route these ground traces between the signal traces to put a coplanar ground on the same layer as the signals, so the signals had a reference point that would help contain the fields. And that's the whole concept here. It's all about the space. By doing this, they created a smaller space than they would have had without these ground routes between these. Again, this is not a great guard trace. This is not how you properly route a guard trace, but it was better than doing nothing. They did ground these at both ends. If you only grounded it at one end, you'd have an electric field shield only. By grounding it at both ends, you will shield both the electric and magnetic field. And that was the concept here. Also notice the ground underneath the IC. That was done because it's not a real high quality IC. There were fields coming off of it, and Dan wanted to help contain those as well. And that was the purpose of that ground. Looking at the other side of the board, they did the same thing. They routed a ground with each pair of lines. And Dan refers to these when he talks to his customers about doing this. He refers to them as triplets, 2 signals and a ground routed together to be able to contain fields. Again, it's all about the space. You've got to contain fields. Notice that they routed power in this particular board, and I hate to tell you, but they did not do a good job of that either. They left the decoupling where it was. Maybe sometime in the future we can do a presentation on proper power delivery, because believe me, these guys did not do that very well, but that's fodder for another discussion. Here's a board that's interesting. It's a 4-layer board with 3 signal layers and a ground. You have signals on 1 and 2, ground on 3, and signals on 4. Well, clearly the signals on 4 have a good reference. Notice the large space between layers 1 and 2 and the ground on 3. Why is that drawn that way? Because that's how 4-layer boards actually look. If you go to your fabricator and ask them, how do you fabricate a 4-layer board? They're going to tell you they use a process called foil lamination. And foil lamination means that the dielectric between layers 2 and 3 will be much, much thicker than the dielectric between 1 and 2 and 3 and 4. And the end result is that these 2 signal layers, 1 and 2, are a large distance from the plane on layer 3. The result is that a lot of people who do this in the automotive world end up with EMI problems. Why do they end up with EMI problems? Because the fields that couple from the signal, now these signals are routed orthogonal to one another. In other words, the top layer would be routed in the X direction and layer 2 in the Y. So they don't route right over each other, they just cross each other. But the fact is, even crossing each other, because the fields have to couple to the plane on layer 3, there's fields from 1 to 3 and from 2 to 3. And in the dielectric space between 2 and 3, the fields from the top signals and the fields from the layer 2 signals couple together. Now, they don't have a tight coupling. If you're not concerned about EMI and you're only doing digital work, this kind of design is almost never going to cause you a problem, because the amount of energy coupling is way too small to cause signal integrity problems. That's why we got away with this kind of design for many years, because people didn't care about EMI until one point in our history when government started driving it hard. EMI problems can occur from such mild levels of cross-coupling that it's ridiculous. Doing this will probably cause a few millivolts of coupling to occur between the signals on 1 and the signals on 2, meaning that you'll develop a 8, 10, 20, 30 microamps of common mode current in the traces on 1 and 2. Why is that a problem? Because as little as 8 to 10 microamps of common mode energy coupled into something which can resonate and radiate is enough to cause a radiated emissions problem, a CISPR 13 emissions problem, or an FCC Class B problem. So this is a problem. First time one of Dan's customers came to him with this, you know what he told him to do? Route layer 1 in triplets. And by routing layer 1 in triplets, it solved their problem. Again, in the digital world, that's an easy solution. What about the analog world? I was contacted one day by a company who sent me this picture, and they said, this is the output of one of the amplifiers in our analog circuit. And this is how it looks when everything's functioning properly. Unfortunately, on the same board, there's an accelerometer sampling circuit. And when that accelerometer sampling circuit is going full tilt, the output of this amplifier tends to look more like this. Just a little bit of noise on that output. And they were, of course, very concerned because clearly things weren't working right. And it was all happening when the accelerometer circuit was sampling. First question I asked them, where are your ground planes? What's your board stack up? Well, needless to say, they had a compromised board stack up. They used the same board stack as the previous slide. Signal, signal, ground on 3, 4-layer board, signal, signal, ground on 3, signal on 4. And the signals on 1 and 2 were cross-coupling like nobody's business. They tried using the triplet concept, but in a sensitive analog signal like this, there's only so much field containment you can get using triplets. They ended up having to go with a 6-layer board, and I'll tell you later in this presentation which 6-layer board they used. It will be discussed later. These kinds of issues need to be thought through carefully when you're designing. Back in the early 90s, 92, 93 timeframe, before understanding these issues, we had an EMI problem from a 6-layer board that looked very much like this board you see. Signal, signal, pair of planes, signal, signal. What was the problem? The same exact problem we just talked about on the 4-layer board. Yes, the dielectrics aren't as thick, but the signals on 1 and 2 are coupling their fields into the same dielectric space between 2 and 3, and the same thing's happening on the bottom side. The signals on 6 and 5 are coupling their fields together in the dielectric space between 4 and 5 to be able to get to the planes. The problem is, of course, this caused an EMI problem for us. We had used this board before and hadn't had issues, and we truly did not understand what was going on. We were just completely puzzled by what was happening to us. So we got together, we talked about it, and decided that the problem was that the outer layer signals were too far from the plane. Of course, that wasn't the problem, but we at the time didn't have the knowledge to understand that. we assumed that the outer layer signals were too far from the plane and they were giving off too much energy, too much differential mode EMI, and that was the problem. So we decided to make it an 8-layer board, move the 6 layers that you saw to layers 2 through 7, and add a plane on the top and the bottom of the board. And of course, if our goal was to quote unquote shield the energy in layers 2 and 7 and 6 and 3, well, how better to do that than to use chassis ground? Wow, what a concept. When we did this, our EMI problem got worse. We were really scratching our heads at this point, trying to figure out how in the world could adding planes to the top and bottom of the board have possibly made the problem worse? Well, the answer is simple. This was the avionics world. And in the avionics world, we figured out really early in life that we could not attach the chassis to the internal ground plane. And there are many reasons why. I don't have time to get into that. We could not attach the chassis to the internal ground plane because of all the tests that we had to go through. And we isolated chassis and internal ground, and yet we provided a chassis plane above signals on 1 and 7. And so the signals on 1 and 7 now coupled their energy into the chassis plane. 2 and 7 coupled their signal energy into the chassis planes on 1 and 8. And the result is the energy had no path back to the driver. There was no connection between the chassis and the ground plane or the power structure of the board. And the end result is that those signals had no way to get back to the driver without spreading out and causing massive energy spread from the fields to find their way back to the driver. Again, the system, quote unquote, worked, but the EMI signature was worse. Now, because we didn't understand the problem, we decided to get together and talk about it some more. And we said, we were guessing, maybe we should just put a ground plane instead of a chassis plane there. That solved the problem. Why? Because of what we just said. It provided a proper return path back to the driver, because now all of the signals were either returning in the power plane or in a ground plane. And by doing this, everything functioned perfectly. All the EMI problems went away. We were completely puzzled as to why they happened. It wasn't until many years later, dealing with the automotive world and their 4-layer boards that were signal plane, that I finally realized why this was a problem. You can't do this. Having a board that has 2 signal layers above a plane on layers 1 and 2 of the board. Now, if the dielectrics are really, really thin, as they would be in an HDI board, you might be able to get away with that. But with thicker dielectrics, as in a 4-layer board or a 6-layer board, really, really a bad plan. And that's the issue there. I was called by a company one day near where I live, and they asked me to come take a look at a problem they had. They had a lone high-frequency analog signal on the outer layer of a circuit board that was a 0 to 9 volt signal. And when the energy in it dropped below, about a half a volt, when the voltage dropped below a half a volt because the energy in the signal was low, what did that mean? It meant the volume of fields was smaller because the energy was low. When it dropped down below about a half volt, they were getting error readings in the analog circuitry, and they weren't sure why. So I went in and talked to them, and I asked the question, has this always been a problem? And they said, no, amazingly enough, the problem cropped up after our last revision to this board. And we have no idea why, because we didn't change anything at all in the area where this signal is. The change was back in a back corner of the board where there were some I/O signals. We did nothing to this area of the board, but we're still puzzled. So we talked about it, looked at the circuit, looked at the schematic, looked at everything. Finally, they brought this picture of the board up. This is the first 4 layers of a high layer count board. They brought this picture up, and I asked the question, what's driving that amplifier at that's driving the high frequency line? And they said, well, that's being driven by 12 volts and ground on layers 3 and 4. And I said, oh, then layer 2 must be a ground plane. And the guy queried it and said, yeah, it was in the original design. Then he went, whoa, wait a minute, it's a 5 volt plane. And I said, there's your problem. And he said, what do you mean there's the problem? And I said, the signal, and I explained to him some of the things we just went over about where energy travels in circuit boards. And after doing that, I said, where's the energy going to travel in this circuit? With a trace on layer 1, where will the energy be? In what dielectric space? And he looked at me and he said, between layers 1 and 2. And I said, exactly. And I said, if the energy travels in the dielectric space between layers 1 and 2, where's the return current going to be? And he said, I'd like for it to be in ground. And I said, but you know it won't be, don't you? And he said, yeah, the return current's going to be in the 5-volt plane. And I said, how does the energy get back to the driver if it's returning in a plane that does not connect to the driver? And he looked at me puzzled and said, oh, good point. I have no idea. And I said, the energy has to spread out across that dielectric space between 1 and 2 to find holes in the plane on layer 2 so it can couple to the dielectric space between 2 and 3 so it can get back to the driver. That's its only means of returning to the driver. And the end result is the spreading of the energy to find its way back. It's coupling into digital circuitry, which just happen to have harmonic frequencies up near a gigahertz, which is where the signal was functioning, had harmonic energy up near gigahertz, which was corrupting the signal when it was at a low enough level. There was enough energy in the high frequency harmonics to cause this thing to malfunction. So then I asked the question, why is that a 5-volt plane? This guy got really mad. And he said, that's a really good question. This was a ground plane originally. And he called someone up and found out eventually when they added some 5-volt buffers in the back corner of the board to bolster the signals at an I/O driver, the guy doing the layout asked, where can I find a plane to put 5 volts in the board? And one of the engineers told him, oh, just change one of the ground planes in the board to 5 volts. So he happened to change this particular ground plane to a 5-volt plane. They changed this back to a ground plane and the problem went away. You see the point and you understand the issue. Then comes the question, of course, can you use the power plane as a return path? And the answer is yes, if it's the power that generated the signal. In other words, this was a 12-volt signal. Had layer 2 been a 12-volt plane instead of a 5-volt plane, they probably wouldn't have had this issue because there would have been a path back to the driver for the fields to couple back to their source. And that's for the return current, actually, from the fields to couple back to the source. And that's the issue at stake here. They reference the wrong power plane. When you're designing circuit boards, you really have to think about where you route. Be very, very cognizant of that. Only reference the power plane that generated the signals. Having low inductance in all pins of an IC is also extremely important. It isn't just the circuit board that we want low inductance paths, it's the ICs. Do these ICs have low inductance? And the answer is absolutely not. These are extremely good examples of terribly designed ICs. Why? Because there aren't enough powers and grounds intermingled with the signals. And the end result is the signals are going to use each other as a return path. In the case of both of these ICs, even power is going to use some of the signal pins, especially in the IC on the left. Even power is going to use some of the signal pins as a return path because that's a lower inductance path than the ground pins of the IC. These are not well-designed ICs. We got away with this stuff back in the 70s, 60s, 70s, 80s, and even the early 90s when things weren't as critical. In this century, we've reached critical mass when it comes to high-speed signaling, and you simply can't use ICs that look like this if you expect them to not create problems. Both of these will create potentially create signal integrity problems and certainly will create EMI issues. This is an IC that was tested by Dr. Howard Johnson. Dr. Johnson retired some years back. Many of you probably remember him. He was a really sharp guy. 15 years ago, he did a study of this FPGA, it's an Altera part, relative to this Xilinx part. And he tested them both in identical circuits. So 2 circuit boards laid out exactly the same, except one was designed for the part on the left and one the part on the right. Notice that the part on the right has a lot more powers and grounds than the ICs on the previous slide. However, in spite of the fact that there are more powers and grounds, there are still areas, as shown by the circles, where there are no grounds or powers mixed in with the signals. And the end result is, what will the signals use as a return path? They'll use other signals. They won't use power and ground. They will use other signals. That's how it works. Mother Nature is very strict in her laws of physics. She does not compromise. If you don't provide a low impedance path, she'll find the lowest impedance path available, and that's where energy will move, in the path of lowest impedance. The IC on the left was so much better than the one on the right that it exhibited 5 times lower noise levels in the IC than the one on the right. Even though the one on the right is infinitely better than the 2 ICs on the previous slide, the IC on the left here exhibited 5 times lower cross-coupling between signals in the study that Dr. Johnson did. He labeled the study, called it BGA Crosstalk. It's about a 15-year-old study. The paper is still out on the internet. Easy to access, wonderful paper. I would seriously encourage you to read it. The point, though, is from a signal integrity standpoint and from an EMI standpoint. It isn't just the circuit board that has to be designed right. It's the ICs that we put on the board. As the great Henry Ott once said, you can do a perfect job of circuit design and a perfect job of layout. And the moment you populate the board with ICs, all bets are off, because there are far too many poorly designed ICs in the world today. Here's a great example of a perfectly designed IC. Dan Beeker at NXP, at Freescale at the time this IC was designed, a group of people overseas in a division of NXP they did a die shrink on a board, of a die I mean, making it was a processor die, making it much, much faster. And they had it originally in a 324 pin BGA package. And the package that it was in, when they put the new die in that package, it wouldn't work. Because they had so much, just as in this slide, they had so much cross coupling between the pins of the thing that they literally couldn't get it to work. They weren't getting good return paths for power, and they were getting terrible return paths for signals, and it didn't work. With Dan's advice, they increased the pin count to 416 pins, adding only powers and grounds. And you'll notice the dark colors on here are power and ground. Dark green is ground, and the dark colors other than green are powers that come into the device. And notice that each of the powers is positioned immediately adjacent to a ground signal. Why? Because inductance is dominated by position, not by size. And the reality is position is critical if you expect low inductance. The only way to get low pin inductance is to properly return power to ground. And the same thing is true with signals. All of the pastel colors in this ball pattern are signal pins. All of them are 1 pin's distance away from power or ground or both. That's what it takes in today's ICs if you expect them to function without issue and without EMI problems. When you're looking for ICs, keep this in mind. It's extremely important. IC companies, thankfully, are getting this. It isn't just NXP who is starting to understand this. I've seen great stuff coming out of Micron and AMD and Intel. There's a lot of companies out there that are starting to do this correctly because they're understanding the issue. So be cognizant of that. On to a slightly different tact. One of the things you want to make sure you do on your board is to group components by function and by family. Analog in its own area, digital in its own area. Not intermingling between the two. You don't want digital signals routed next to analog signals. You want analog to be contained in one area, digital in another. You want devices operating from different voltages in different areas. Why? Many reasons. One, you don't want 2.5 volt signals routing next to 5 volt signals because the cross coupling will be much worse than from another 2.5 volt signal. Plus, you don't want to have multiple power planes just to feed power to these devices. If you break devices up by voltage, you can have fewer power planes because you can split a plane up into many, many voltages. I've put as many as 18 voltages on a power plane before and gotten perfect performance and good EMI signature out of the system. Put devices that operate at different frequencies in different areas. So the high frequency analog in one area, the low frequency analog in another, and so on and so on. Put stuff together by function and by family or by voltage within a family. In other words, the processor with its memory and all of its associated devices and so on. I'm sure everybody's aware of that. If all the ICs, place all the ICs near route to connectors, place them near connectors. So one, you don't have to filter going out of the connector if you're just going board to board. And two, so that you won't pick up common mode energy in the traces, coupling them through the connectors into wherever they're going. So as much as possible, put drivers as near connectors as you can. This is a good thing to keep in mind when you're setting up component placement. Keep all routes confined to the stage or section to which they are assigned. All the digital in the digital area only, all the analog, low-level analog in the low-level analog area, all the high-frequency analog or microwave in its own area, and so on and so on. If traces are isolated to sections, you typically do not have to split planes as long as you are operating above the audio range. If you have stuff that's in the very low end of the audio range, for that particular circuitry, you may have to split the ground plane. But at high frequencies, it is not necessary to split ground planes. One thing to keep in mind, I mentioned analog and digital in their own areas. If you can keep the devices and routes separated by 20 times the distance from the layer 1 signals and components to a plane on layer 2, assuming that you're putting a ground plane on layer 2. And oh, by the way, speaking of good grounding concepts, in your board stack, if you have signals on one, components and signals or whatever, layer 2 is ground. That's what good board stack mandates. Layer 2 is ground. So, with that thought in mind, if you put a ground plane on 2, whatever is on 1, components and signals, if you can separate the analog and digital signals from one another by 20 times the dielectric spacing from 1 to 2, and place the A to D, D to A, whatever is coupling the two circuits together, at the point where they cross, then it won't be necessary to split ground. Again, unless you have extremely low frequency analog in part of the analog side of the board, then it may be necessary. Beyond that, it shouldn't be necessary to split grounds. One of the things that's recommended by a lot of IC companies is to isolate things like video controllers, for example, into their own section of the circuit board. And they recommend splitting power and ground below their ICs in that area of the board and coupling power and ground from the main area of the board using pi filters, some type of low-pass filter, an LC or an LCC type of structure to couple power through the splits to the other side of the board. Is this a good idea? Well, if you didn't care about signals getting in and out, and you could make the area of power and ground under the sensitive IC large enough, then yeah, it's probably not the worst idea in the world. But what about the reality of getting signals in and out of the board? How are you going to route data and address from that isolated IC into the other area of the board without crossing a split plane, which we've already discussed is a terrible idea? Well, the answer is you can't. In reality, all you need to do is split just the power. Think about where energy travels. Energy travels in the dielectric space between the power plane and the ground plane. It's a transmission line like any other transmission line. And the noise energy also travels in that same dielectric space. If you break the transmission line, either the ground side or the power side, that will be sufficient to prevent the noise energy from coupling across the split. You can leave a solid ground plane and just split power. I've read many, many books and articles over my career of people who have tested these concepts and proven repeatedly that you don't need to split both power and ground, just split power. Keep that in mind for the future. Now, when you do that, if you have power and ground close together, can you route a signal across that split power, assuming, one, it's the power that generated the signal, and two, that it's the same power on both sides, which is, of course, what we were just discussing. Can you do this? Well, the answer is yes, if the power and ground planes are within a very tight space, about 8 mils, about 0.2 millimeters. If you can keep the power and ground planes within 0.2 millimeters of one another in terms of dielectric spacing, then the fields will couple through that opening in the power plane to the ground plane below. And you'll get a little bit of field spread as that happens, but the field spread will be minute enough that it's not going to cause a problem. Is it an impedance discontinuity? Of course it is. But as long as it's a small gap, is it a discontinuity large enough to create a problem? The answer is no, unless it's an extremely high-speed signal. And for that reason, I wouldn't do this with gigabit level signals. And I wouldn't do it if for some reason you are forced to split both power and ground. You simply can't route across the split if you split both. And it's not a good idea to do this with very high frequency stuff as well. What if the planes aren't close together? What if it's something like a 4-layer board? Dr. Bruce Archambault, who spent a large portion of his career as a senior fellow at IBM in the Carolinas in the United States, ran a study one time where he tried this. He tested this on a 4-layer board. Remember, the dielectric on a 4-layer board is very thick between layers 2 and 3. So he put power and ground on 2, ground on 2 and power on 3. And he set up a signal and a receiver on layer 1, and he fired it up, driving a signal from the IC on the left to the IC on the right, referencing a solid ground plane. Using a near-field probe, he measured the energy radiating off the board. Again, he used a near-field probe because he wanted to be able to get the maximum sensitivity reading of how much energy was coming off of this board. He then turned off this driver and receiver, turned on an identical driver and receiver on the bottom of the board that happened to route across a split power plane. And he then fired that up and made a second measurement of EMI coming off the board. And of course, as everybody knows, you can put a capacitor across the split planes and that'll solve the problem. So he said, all right, let's try that. He put one set of capacitors across the split power planes to be able to bridge them at frequency and see what would happen. He made a third measurement. He then put a second set of capacitors and made a fourth measurement. These are the measurements. This is the measurement with the signal referencing the solid ground on layer 2. And you can see as it goes up in frequency, it gets worse, which is exactly what you would expect. It's harder to contain fields at high frequencies. This is the measurement of the same thing referencing the split power plane on layer 4 of the board with a split power plane on layer 3. There's anywhere from 20 to 30 dB higher level signature, again, depending on frequency, with the signal crossing the split power plane than there is with the solid ground. And the message here is, can you route across the split power plane? The answer is yes, but only if they're close together. Power is close to ground. And yes, if the signal is not terribly high frequency. In this particular case, you can see routing across the split between layers 3 and 4 of a 4-layer board was an absolute living disaster. With one capacitor in, it got better at low frequencies. Why would that happen? We'll discuss that in just a moment. With two capacitors in, it got slightly better at all frequencies, but was still horrible at high frequencies. At high frequencies, this does not work. You cannot route across split power planes in circuit boards if they're far away from a ground plane in a circuit board at high frequencies. Just not a good plan. And notice the maximum frequency that he tested to was only a gigahertz. So with signals well up into the gigahertz region, it's probably going to be worse. Why do capacitors misbehave at high frequencies? They have an impedance due to capacitance that goes down as you go up in frequency. They have an impedance due to inductance that goes up as you go up in frequency. At the point where these two cross, they are the same impedance. They're 180 degrees out of phase, and they cancel each other. This is called the self-resonant frequency of the part. It's a capacitor and an inductor in series, and there's a small amount of resistance. So the overall impedance curve of the device at frequency looks something like the red line shown here. Capacitors do their best work at self-resonant frequency, obviously. To the left of self-resonance, there's still a capacitor, and they still behave like a capacitor. As frequency goes to the right of self-resonance, as you go up and up in frequency, as you can see, they're becoming less and less a capacitor and more an inductor. And the result is that they don't transfer energy well at high frequencies, and that's why adding the capacitors offered no benefit in the high frequency portion of the radiated emissions from that board. So keep all that in mind when you're routing circuit boards. Do not route signals on a ground plane layer. For example, you should never split the ground plane to route signals on them. If you absolutely must, if you have a really low layer count board and you have no choice but to do this, obviously keep it as small as possible. I have done this in low layer count boards in the past. I try not to, do it when I have to. I never route more than 2 or 3 signals across that split. Ideally, you don't want to route more than 2 because the 2 signals referencing the plane below, the red plane below, if you put a small split in them, they'll branch out a little bit to go around the split and then couple back together underneath the signal as they should. And you'll get a small expansion of fields, but it won't be too large. You make this a large split, and it's just like routing across any other split in the ground plane. It's going to get you into trouble. With really low frequency signals like control lines, the good news is you can route those through 0 ohm resistors, because at low frequencies, a 0 ohm resistor is truly 0 ohms. You should not do this with high frequency signals, because at high frequencies, a 0 ohm resistor has way too much inductance to be 0 ohms. It'll be many ohms at higher frequencies. So this is a bad plan for high frequency signals. Neither of these is ideal, of course, but the reality is in the low layer board count world, sometimes these things become necessary. So keep that in mind. Speaking of layers and changing layers, why do we change layers? Well, the reason we change layers is to change direction. We route maybe layer 1 in the X direction, and then the next signal layer down, if it was layer 3, we'd route in the Y direction, and so on down through the board stack. So when you change layers, you do it to change direction. Ideally, if you're going to change layers, the best way to do it is to go from layer 1 to layer 3, assuming a ground plane on layer 2. Why? Because with a ground plane on layer 2, where are the fields? They're in the dielectric space between the signal on 1 and the plane on 2. And when you open up the plane to put a hole in it for the via that's carrying the signal energy, you create a space through which the fields can travel to get to the dielectric space between the signal on 3 and the plane on layer 2. And that keeps the fields tightly coupled as you move from layer to layer. You get no field expansion when you do this, and you don't have any worry about fields spreading out and coupling into other things. People ask me all the time, why would circuit A couple into circuit B? They have no commonality between them. There's no connection between them. And the answer is because they're physically close enough together that you somehow have not contained the fields, and the non-contained fields couple from A to B. Same thing happens here. If we allow the fields to expand as we change layers, other vias that are in this area will simply have that energy coupled into their signals. And those signals will then couple into this signal and so on. So when you can route between either side of a ground plane, or in this case, it could be a power plane, it works out just fine. What if you have to change layers from one ground plane to a different ground plane? In this particular case, going from, say, layer 1 to layer 10 of a 10-layer board with ground on 2 and 9. The ideal way to do this is to put a ground via in the circuit right next to the signal via. You want a ground via as close to the signal via as you can get it. If this were an RF board, I would probably surround the signal with 4 ground vias, because RF boards are typically low density and you have the ability in an RF board to do that. In a digital board, you're not going to have that ability, but at least put a ground via nearby. Here's a picture from another study done by Dr. Howard Johnson, where he illustrated what happens when you have a ground via versus not having a ground via. And what's going on here, this is a 4-layer board with 2 ground planes. The energy is in the dielectric space between 1 and 2. When it gets to this hole, it couples through the hole and then couples back and forth between the signal via and the ground via. It's all the fields as it's going through the dielectric are coupling between the 2 vias. And when it gets down to layer 3, the fields establish a current in the top of layer 3, the energy couples through the hole, and then continues on in the dielectric space between 3 and 4. Notice that the fields between the vias are coupling across the outside of the vias, not the inside. There is no current flow inside a via. People ask me all the time, I have to fill vias because I'm going to solder mask over the vias. Can I fill them with non-conductive fill? The answer is you can fill them with peanut butter. It doesn't matter what you put in the vias because there's no current inside the via barrel, so it doesn't matter what is in the via barrel. The only thing that matters is what's on the outside, and that is metal. What if you're going to couple from a power plane to a ground plane? Well, as we just discussed, capacitors can move some of the energy. If you're lucky enough to be dealing with microcontrollers only and other low frequency devices, you can probably do this and simply put a decoupling cap near your vias. So if you do all your vias near the ICs, there's going to be decoupling caps nearby, you'll be fine. If you drop a via in the middle of the board somewhere, then ideally you would want to put a decoupling cap at that via. What if it is a higher layer count board? What if you have a higher frequency IC as opposed to a microcontroller? What if you had a high-speed microprocessor or FPGA or high-speed memory, all of which, by the way, have nominal operating rise and fall times of about 500 picoseconds, which means that their upper end frequency isn't at clock frequency, it's up close to 1 gigahertz. So most of today's processors have harmonic frequencies that extend to 1 gigahertz or 2. So how are you going to move that energy through that capacitor? Well, you're not. So the reality is when you have high frequency energy to move, again, if it's a high layer count board, and if power and ground are very close together, as long as they're within 0.2 millimeters of one another, dielectric spacing, you can likely do this without incurring enough field spread to be concerned about it. But what if it's a low layer count board, such as a 4-layer board, where you have a thick dielectric between layers 2 and 3? How is that energy going to move between layer 2 and 3 without spreading out? Well, the answer is it isn't. Because the dielectric thickness between layers 2 and 3 of a 4-layer board is typically 3/4 of a millimeter to a millimeter thick. I mean, it is a very thick dielectric. And those fields are going to spread out for many millimeters in all directions, just trying to, because what happens, you get a displacement capacitance, you get a displacement current, created by the capacitance of the two planes. The power plane and the ground plane form a capacitor. And when they're very close together, they have a fair amount of capacitance. So the fields don't have to spread very far, as shown in this picture. The fields only have to spread a very short distance to form enough capacitance to couple between them. When the planes are very far apart, as a 4-layer board, or as in a 6-layer board with power and ground on layers 2 and 5, there will be such a large dielectric that they're going to spread out for a large distance. What's going to happen? You're going to have other vias within that same distance, and those vias are going to couple their energy into this via's energy, and all of these vias are going to be cross-coupling into one another, saying, "Hi, how you doing? Let's have a party." "Yeah, let's do. Let's raise heck and really cause problems," and they will. Now, from a signal integrity standpoint, you can get away with this all day long. There are a lot of high-speed signal integrity experts, and I'm not going to name them, but there are two in particular I'm thinking of. One of them works for a simulation company, and the other one is an independent consultant who focuses mainly on signal integrity at gigabit speeds. And the truth is, at gigabit speeds, the reality is the spreading fields here don't cause enough harm to create an issue. Do you need return vias? Do you absolutely have to have planes close together when you're transferring signals like this in a very high-speed board if all you care about is signal integrity? No. But if you care about EMI, you really, really should think about this. And if these are analog circuits, you should think about this very seriously, because you don't want analog circuits as sensitive as they can be to cross-couple to one another. So keep that in mind when you're doing this. Let's get into a short discussion on board stack, and then we'll be done for the day. I have a good friend, Lee Ritchie. Many of you know Lee Ritchie by name. Lee had a customer, a client, who came to him once and said, "Lee, we have a 6-layer board that has an EMI problem." He tracked it down to a power distribution issue, and he talked to him about going to 8 layers, and they said, "Nope, not going to happen. Our management will never allow it." So he said, "All right, let's rethink this." And he then went back to him and said, "Hey, I want you to try something. The signal layers are layers 1, 3, 4, and 6. On layers 1 and 3, I want you to pour copper, and I want you to attach that copper to the ground plane on layer 5. And I want you to pour a lot of copper in all the open areas of 4 and 6, and I want you to attach that with lots of vias to the power plane on layer 2. And then I want you to build the board and test it again and see what happens." In doing so, the measured capacitance of this board before adding the copper pores was only about 500 picofarads. The measured capacitance after the power pores was 4,100 picofarads. And that helped improve power delivery by offering some capacitance that was capable of delivering high frequency energy to the ICs. But the reality is 4,000 picofarads of capacitance, or 4,000 picofarads of capacitance is just not very much capacitance compared to the discretes we put on the board. These planes, the importance of having the increased plane area on the board wasn't capacitance. More than anything, it was inductance, because the inductance of these planes went down by a factor of 8. So there are 3 reasons that the EMI signature got better. 1, more capacitance in the board. 2, lower inductance in the board. And I'll cover the 3rd reason in just one moment. We'll get to that in a second. This is the EMI signature of that board before and after the copper pores. The green lines show the EMI signature before the copper pores were added. The blue lines show it after the copper pores were added. Notice that the EMI signature is considerably better after the copper pores were added. Why? Better power delivery due to lower inductance, and there's a second reason, which I will discuss in just one moment. In fact, I'm going to skip this slide and come back to those in just a moment. I'm going to bring this up. Look at the picture on the right. This is a 6-layer board similar to the one Lee had with his client. Prior to putting the copper pores on the board, he had what you see as the 6-layer board on the right here. Signal, power, 2 signals, ground, signal. not only was power delivery poor, but look at the dielectric space between the power plane and the ground plane. I ask people all the time, where does power come from in a circuit board? And the answer I get back from them all the time is from the power plane. Incorrect answer. The answer, where the power comes from, it comes from the dielectric space between the power plane and the ground plane. That is a large dielectric space on layers 2 and 5. So all of the power energy is delivered to the ICs from that dielectric space, which has low capacitance and high inductance. But most of all, there are fields, power fields, occupying that space. What else is occupying that space? The fields from signal lines on layers 3 and 4. So as those signals are generated, their fields also occupy the same space as the fields that are delivering power, which means they induce currents into one another that create coupling of common mode currents into the signal lines and noise coupling into the power energy driving the IC. So going back to the board after Lee had them redesign it, you'll notice what's happening here. There are still signals on 3 and 4, but they now are referencing, again, still the power on 2 and 5, but also there is power and ground poured on 3 and 4. So now we're not getting power from 2 and 5 only dielectric. We're getting power from the dielectric between 1 and 2. We're getting power from the dielectric between 2 and 3, and 3 and 4, and 4 and 5, and 5 and 6. So the power delivery is coming from 5 separate, smaller dielectric areas. And the end result of that is that the fields from power are not interfering with signals and vice versa. And that's the third reason that Lee's board behaved better than the previous ones. Let's go back now. There's a couple of things I want to cover on this slide here. Back in 1994, I was involved in a project where we had a 4-layer board that had a serious EMI problem. And we redesigned the board to put all the signals on the inner layer of the board. Before we redesigned it, the outer layer of the board was components and signals, and believe me, there was no room out there for anything but components and signals. When we moved the signals to the inner layers, there was a lot of area on the board, on the outer surface of the board, where we could pour ground. And when we moved the signals to the inner layer, we made sure that they were moved so they were sitting under that ground on layers 2 and 3. We then poured the open areas on layers 2 and 3 with power so that we had power on layers 2 and 3 referencing ground on 1 and 4. The end result is that we actually got a lower impedance power delivery structure with this 4-layer board than we did with the conventional 4-layer board having power and ground on 2 and 3. Reason? We had higher capacitance in the power bus and lower inductance. And now all of the signals referenced ground, so when we changed layers, we didn't have to worry about trying to move energy across a large dielectric space that was going to cause interference. We lowered the EMI signature of that board by 12 or 14 dB. It was a major improvement. Every 4-layer board that I have designed since 1994, I've either used the 4-layer board on the left or the one on the right. Unfortunately, the one on the right can only be used when you have a really low density design, because you're going to have to be able to get ICs and signals and poured power on the top of the board to make this thing work. And that's only going to happen with a low density board. But when you have low density, this is a great design to use. So something to keep in mind. This is what a 4-layer board's power and ground planes look like when you use layers 2 and 3 of the board to deliver power. This is what they look like when you do what's shown in the figure on the left here, with signals and power on 2 and 3 and ground on 1 and 4. The plane's overall impedance drop by a huge amount. It's not a 10-to-1 drop, but it's a reduction of 60–70% in the overall power plane impedance. And that is massive when it comes to getting good power delivery. And then going back to this, these are the 6-layer boards we were just talking about. Obviously, the one on the left is the one we did in the 1990s that we learned the hard way not to use. The one on the right is the one Lee had his customer redesign. And this, of course, on the right is the redesign of Lee's particular board. This is the power planes of a 6-layer board with power and ground on 2 and 5. You can see it's not a very low impedance. We don't even achieve 1 ohm impedance with these planes in this structure. Just by redesigning it and adding the copper pores, the power bus impedance reduces by an order of magnitude, a factor of 10 to 1 reduction in the overall impedance. 1 or 2 more slides and we'll be done and can hopefully take a couple of questions. I'm going to skip through these for the moment because I want to get to this slide. This is an 8-layer board recommended by a major IC company, and I won't mention their name. When I'm doing a smaller class in a company, I will generally talk about who this is. But in their app note for this particular processor, it was a 1300 pin processor, and they said, we know that some people need low layer count boards, and this is the lowest layer count board we were able to create to make this IC work. And the truth is, I can believe that with enough on-die and on-package capacitance that they made this board work. But one thing I'm certain of, this board could not pass EMI testing. Ask yourself the simple question, where does the power come from in power plane 1? It comes from the dielectric space between layer 4 and layer 2 and between layer 4 and layer 5. And most of the field energy in power 1 is going to couple to layer 5, which means what? That you're going to get the return current from power 1 in power 2. Is that what you want in the board? Do you think that's going to deliver energy cleanly without noise problems? The answer is no. The answer is absolutely no. There's no way you can do this. Now, you could put a thick dielectric between power plane 1 and 2, and then power 1 would couple only to the ground plane on 2. And that's the good news. However, look what else is going on there. There's a signal layer between them, which means that the dielectric space from where power comes, there will also be signal fields in that same space. They will couple to one another, and there will be EMI problems. This is what you absolutely do not want to do. Thank you very much for attending. If there are any questions, please let us know, and we'll try to answer them. Nothing? Okay, thank you guys. Really appreciate it. If you have questions in the future, direct them to Altium, and they will direct them to me, and we'll try to get them answered. Thank you so much.